All right, 1.3. We are going to continue our discussion of displaying quantitative data, and we're going to talk about how to do that with a lot of different numbers, a lot of different ways that you can display and summarize quantitative data with numbers. So we're going to talk about measures of center. What does SOC stand for? Very good. And center. When we talked about center, what two values did I say you could use? Mean and median. You got it. All right. Cool. Mean and median. Now, can you guys tell me, how do you find the mean? You add up all the numbers and divide by the number of numbers, right? Ladies and gentlemen, I'm about to show you the very fancy statistical formula for adding all the numbers and dividing by the number of numbers. It doesn't change that you're still just going to add up all the numbers and divide by the number of numbers, okay? So here we go. The notation for mean is X bar. Oh my gosh. When you see X bar, you should know that that means it is the average of the X's, or the numbers, right? So X bar equals, you ready for it? The summation of X sub I divided by N. Miss Lakey, you just broke my brain. This little sigma, this is sigma. This is a capital sigma. It stands for sum up or add up. What do you have to add up? All the X numbers, all the X values. X sub I, meaning it's X number 1, X2, X3, X4, X5. It's X for however many numbers there are. It's just like a subscript for labeling. Yeah. All right, so we're gonna add up all the X's and then do what? Divide by the number of numbers, which is N, which is your sample size. So we're gonna add up all the X values and divide by the number of numbers. It's a fancy way to show exactly what you've been doing since elementary school. Any questions? Perfect. But what's most important here? X bar. X bar is the notation for mean. Alrighty. Here are 15 randomly selected SAT scores from students in the enrolled AP Statistics. We need to calculate the mean of this data. Ladies and gentlemen, I do not want you to do 910 plus 900 plus 1090 plus 1080. I don't want you to do that. Here's what I want you to do. I want you to put the data in your list. Do you remember how to put data in a list? Yes. How do you do it? Stat, edit. Stat, edit. Stat, edit. There it is. All right, I want you to input this data. Go. What?
So what do we do if we don't have that calculator?
What calculator do you have? Then you're on your own. On my Canvas course, there is a button that says Calculator Resources. If you click on Calculator Resources, there is an Inspire user manual for stats. It goes in order of what we do. So it starts with chapter 1 and how to do this kind of stuff and goes from there. You are more than welcome to utilize that. I can tell you this. So if you know this much about the Inspire, this is what I can tell you. To do this, you have to go to a spreadsheet. And then you have to input the data into the cell, into the spreadsheet, down one column. And then you have to do something about menu, calculate stats, something. So that's about as much as I know for how to do this. All right, everybody have their data input? Yeah. If I don't have my phone. All right, here we go. We are now going to tell our calculator to calculate for us. So we're going to go back to stat. We're going to hit the right arrow to calc. and we're going to hit enter on number 1, one variable stats. The list should say L1. If it doesn't say L1, and if you hit second and the number 1, it will say L1. Frequency list. You can leave this blank. This is going to be when we have probabilities, but we are not going to get there for a while. So you can just leave it blank and then hit calculate. Boom! What's the very first thing you see? X bar. What is X bar? The mean. The mean of this data set is 1094. X bar is 1094. Now, before we go on, I do want to talk about what else is on the screen. The sum of X. Look, we just read that notation, didn't we? The sum of all the X's is 16,410. If you look down a little further, it says N equals 15. That means there were not 15 numbers. So if I took 16,410 and I divided by 15, guess what I would get? 1094. Bet. All right, the sum of X squared. If you take each X value and you square it and then add all those up, you get that big number. We will never use that. It is not useful. So, but it's there. Sx and this sigma X, this is another sigma, it's a different sigma. Sx and this other X, those have to do with standard deviation. We'll talk about that next week, but for now, just ignore. Minimum, what's the minimum number in the data set? 900. Q1, we're going to talk about what Q1 stands for here in just a minute. Hey guys, there's an arrow pointing down. That must mean there's more to see. Hit the down arrow. There's the median, 1080. Q3, we'll talk about in a few minutes. Maximum, the maximum number is 1580. This is how you should be finding means. Put all your data in a list, do stat calc 1. Don't be trying to add them all up on a screen and then divide, blah, blah, blah. Don't do that crap. So this is how you're going to do it. All good?
Why would you try to do that?
Awesome. So 1094, that is our mean. Any questions? All right, the next thing says, or do you think there are any potential outliers? Do you guys, what's an outlier?
1580.
Woo, 1580. Some smarty tardy got a 1580 on their SAT. We're going to take that out of the data set. So go back to your list. Stat edit. Arrow down until the 1580 is highlighted, and then just hit delete, which is right above stat. It goes away. Now, recalculate. How do you recalculate? Stat, calc, 1, enter, enter, enter. Boom. Here's our new mean, 1059. 1059. Huh? Who, what? Who, what, when, where? All right. So, X bar was 1094. Yes, we thought that 1580 was an outlier, so our new X bar is 1059? 8? 7? 9? 9. 1049? 50, whatever, it's fine. 59. Okay. All right. How did removing that potential high outlier, how did that influence the mean? It went lower. By how much? By like almost 40. Is 40 points on the SAT a big deal? Yeah, so like this significantly changed our mean, right? So the mean decreased. The mean decreased. Okay? So yeah, there was a pretty big change, a change of 40. That's a pretty big change for an SAT score, okay? All right. Going back to the original 15 numbers, we're going to now add in a low number of 775. Somebody had a tough day. All right, so how do you get back to your list? Stat edit. You can just go to the bottom of the list and put the 1580 back in. Put the 1580 back in. Don't forget to put the 1580 back in. And then add in another number of 775. Whoops, not 7,000. 775. Add in 775. And now we're going to recalculate. How do you recalculate? Stat calc 1. Enter. Whee! 1074. 1074.
Calculator is like it keeps going 3 above 3.
So one of your numbers might be different.
No, I checked.
Oh. What's it saying?
Oh wait, you're in geometry. No.
The mode doesn't matter.
Okay, well, where's Scott?
I don't know. That's interesting. All right, so we went back to the original 15. We added in that 1580 and we added in a 775. And then what happened to the mean when we added in 775? It decreased to 1074. 4. It decreased to 1074. So, what we have just experienced here is that when I start changing those outer extremes, those maximums and minimums, it is going to very heavily change the mean, right? We're going to be influencing our mean quite a bit. So our mean is sensitive to our extreme values in our distribution. So we say that is non-resistant. Non-resistant. When something is not resistant, it's like it can't help itself, right? It has to do what is being told. And so we're telling it to change its numbers, and it's changing because it is being affected by those extreme observations. So this is non-resistant. The mean is not resistant. It is going to change. Got it? Awesome. What is the other way that we could do center instead of mean? Median. Here are the SAT scores again. Oh, look, these are in order for you. So, you probably already saw the median. It was on your calculator screen. Yes, you can do stat calc 1 and you can get the median. But just for funsies, we could also do this whole marking off thing here. Whee! This is so fun. Yay! All right, there's our median. There is not any special fancy notation for median. You can just use MED. That's totally appropriate. All right, so what if we took out the 1580? What would happen to the median? So the only thing that would happen would then these two numbers here would be the middle, and I would have to average them. So basically the median would go down by like half a step, if you will. And that would be the average of those two numbers. It looks like it would still be 1080 because both of those numbers are 1080. In a large data set, I'm talking about hundreds of numbers, you're going to have a lot of numbers that are going to overlap or be the same. And so a lot of times your median is going to just be the same number like this, okay? So if we remove that potential outlier, the new median is still 1080. All right, so put that number back, put 1580 back. We're back to this 1080 here. And again, if I add in the 775, now my median is still 1080. So it still stays the same. The median is not affected as much by the extreme values. It is going to be affected if you have a small data set, but again, in large data sets that we usually work with in stats, it's not going to change very much. So because of that, our median is not going to change much. So the median does not change much, if any. So because of that, we can say that the median is not sensitive to extreme values. So we would call the median resistant. You got it.
Wait, so what does non-resistant mean?
Non-resistant means that it is going to change. It is affected by changing values. The median, resistant, it stands its ground. The mean, it's like, whatever, I'm changing whatever you guys say. Let's just do it. Sounds good to me. All right, let's talk about where the mean and the median is when we're looking at certain shapes, certain data shapes. What shape is this far left graph right here? Woo.
Feet.
Feet, yes, feet. Feet. All right, what shape is this one over here? Left skew. What shape is this?
Roughly symmetric.
Approximately symmetric. What shape is this? Right skewed. Okay. Notice the median, or I'm sorry, notice the mode. Notice the mode. Where is the mode in all three of these? At the peak, okay? Again, the mode is when a data value is being stacked up over and over and over again because it's repeating and it creates a peak. So your mode is always going to be at the peak of a distribution. Does that make sense? Perfect. All right, median. The median is going to be it's going to cut the distribution in half, okay? 50% on the left, 50% on the right. And so the median doesn't have to come that far from the mode in order to cut the data in half, 50% and 50%. The median is going to be just slightly off from the mode, but the mean, if you look at the mean comes way down. Why is that? It's not resistant. It's trying to average in these extremely low numbers. The further down your low number is, the further down the mean comes. So in a left skew distribution, your mean will always be lower than your median every single time. So this is left skew. Your mean is less than your median. Your mean is less than your median. So, how is this helpful? Check this out. Let's just say I tell you that the mean of a distribution is 23 and the median of that same distribution is 47. And this is the only information I give you. I tell you nothing else. I say, hey guys, I have a distribution that has a mean of 23 and a median of 47. You can look at that and see that the median is much bigger than the mean, and you could then tell me that I have a left skew distribution just from those two numbers. Yes?
When it asks for center, which one do we take?
So when it asks you for center, if it is a skewed distribution, you're going to use median because that's a better indicator of the center in a skewed distribution because the mean was too affected by the skew. In a symmetric distribution, we prefer to use the mean, but obviously the median will work because it's in the center as well. So the mean and median are going to be in the center in a symmetric distribution. But yes, anytime you have a skewed distribution, you're going to want to use the median because it's resistant to those outlying values that are kind of messing up your data a little bit. So in a right skew distribution, what is going to be true about the mean versus the median? Good. In a right skew, your mean is going to be greater than your median. So an example might be, I don't know, let's give a mean of like 150. And maybe the median is like 127. Okay? Just from that data, you could tell me that that is a right skew distribution. Just because of the fact that the mean is greater than the median. The mean is always pulled out to whatever direction it's skewed. So if the mean is lower, that means it was pulled to the left. That is a left skew. If the mean is higher than the median, it was pulled to the right, so it's right skew. Any questions about that? Awesome. And Ayala already answered this question for us right here. When should we use the mean versus the median? Mean is going to be approximately symmetric data. Median is going to be for your skewed data. And that's going to be generally speaking what you should do. And that's because of the resistance of the median. The median is resistant, and so it's not influenced by that skewed data. I am not saying that you will never have a skewed distribution where you use the mean. You will have the mean. It's going to happen. But I'm just saying, generally speaking, if you have a skewed distribution, let's go ahead and use the median if you can. If you can't, then you just do what you can. All good? How we feeling? All right, let's talk about spread. Woohoo! What does SOC stand for?
Outlier, center, spread.
Very good. All right, so when we're talking about spread in SOCs, we've been listing the low to the high values of the distribution because that helps us know where it is on the number line. We can quickly get the range and whatever else we might want. But there's lots of other ways to do spread or variability, all right? So if I'm talking about how varied the data is, there are lots of ways we could do it, and that includes range, which you guys know how to do, IQR, which we're going to learn, and standard deviation, which we'll learn. So range, it's the difference. It's the difference between the largest and the smallest observation. Most people would say it's calculated as max minus min. It's the difference between the largest and the smallest observation, max minus min. So let's think about range for a second. Max minus min. Would range be resistant?
No. Yes. Yes.
Non-resistant.
Wait,
If you add a really
less
high-
resistant than median.
Okay, here is a data set, 1, 2, 3, 4, 5. What is the range of 1, 2, 3, 4, 5? 4. I'm going to change 5 to 50. What's the range now? 49. Did the range change? A lot. Is the range resistant?
No.
Nah, bro.
Can't believe Daniel said resistant.
I didn't say that.
I didn't hear that.
It was a kill.
It was totally a kill.
Wait, hang on. A kill. Wait. I thought you were a kill.
All right. Quartiles. Do you guys know what a quartile is?
No, when I tried Google,
Yeah,
we
25%.
were.
All right, here's quartiles. First quartile, also known as the lower quartile, also most commonly known as Q1. It is the value in the data that is larger than 25% of the observations. It's the first 25% cutoff. Quartile 2, also known as the median. We are going to continue calling it the median. It is technically the second quartile, but it's the median, okay? It is larger than what? 50% of the observations. The third quartile, also known as the upper quartile, most commonly known as Q3. It is larger than 75% of the observations. Miss Lakey, you forgot the fourth quartile. What would be the fourth quartile? So it would be the maximum number. Guess what? I'm going to keep calling it the maximum. So median and maximum are going to still be what we call it. All right, how do you calculate quartiles? Here we go. Arrange the data in ascending order and find the median. Here's an example. 1, 2, 5, 7, 9, 11. Okay, cool. 1, 2, 5, 7, and 9, and 11. I've got them in ascending order. What is the median of that data set? 6. It would be right here, right? Here would be the median. The median would equal 6. Cool. Next thing I would do. Q1 is the median of the observations whose position in the ordered list is lower than the overall median. Basically, what that says is Q1 is the median of the lower half of the data. So here's the lower half of the data. What's the median of that lower half? 2. So Q1 would equal 2. Q3 is the median of the observations whose position in the order list is higher than the overall median. Again, it is the median of the upper half of the data. So what would be Q3? 9. 9 would be Q3. Very good. So Q1 is 2, Q3 is 9. That's how it works. What if there is an odd number of numbers? So 1, 2, 5, 7, 9, 11, and 13. All right, what's the median? 7. The lower half is these 3 numbers. I don't include the median. And so what's the Q1? 2. The upper half are these three numbers. So what's Q3? 11. Do you guys have any questions? Is this so easy? Let's talk about IQR. IQR. The IQR measures the range of the middle 50% of the data. It is the range of the middle 50% of data. It is the range of the inner quartiles. So, how do you think you calculate IQR? You find the distance between Q1 and Q3. It works very similar to range, max minus min, except you're going to do Q3 minus Q1. So you're going to take Q3 and you're going to subtract Q1. All right, so earlier, here's what we had. 6 was our median. This was Q1. This was Q3. Okay? What is the IQR of this data set? 7. We just take Q1 and we subtract Q3. This is our IQR. IQR would be 7. Is IQR resistant?
Yes. No. Yeah. No. I don't know. Just as resistant as the median.
Here's what I love. I love that I ask a question, you guys confidently answer it, but just because I don't say anything, you start questioning your life. You're like, what? I'm not. The answer is yes, it is resistant. You guys were right. I just like messing with you. Yes, it's very resistant, in fact. You know why it's resistant? I'm literally cutting off the outside 25% when I'm finding the IQR. I'm looking at the middle 50% of the data. This outside 25% data has no effect on it. None at all. So that number could be 110 or 1,100. This could be negative 301, and it don't matter. None of that's going to affect the IQR. The IQR is very resistant. Also, what is the IQR based on? It's based on medians. Is the median resistant?
Yes.
Yeah, bruh. So guess what? IQR is also very resistant. So, yes, IQR, very resistant. We like IQR. Cool? Cool. 5-number summary. Woo! The 5-number summary. The 5-number summary. How many numbers do you think are in the 5-number summary?
6.
I really wish it was like 6, but it's not. All right, so minimum, Q1, median, Q3, and the maximum. These are the 5 numbers that make up the 5-number summary. So here's an example. 1, 2, 6, 9, and 11. There's my 5-number summary. The 5-number summary usually does not have commas in between the numbers. It just has a little bit of space. And it would literally say, here is the 5-number summary. 1, 2, 6, 9, 11. And you go, okay, cool. And so what is the 1? The minimum. What is the 9? The 9, Q3. What is the 11? Maximum. What's the 2? All right, everybody understand that?
Yeah.
What's the IQR? IQR would be 7. Okay, cool. I have a question for you. What percent of the data is between 1 and 2? 25%. What percent of the data is from 2 to 6? 25%. What percent of the data is between 6 and 9? 25%. What percent of the data is from 9 to 11? That is why they're called quartiles, because there's 4 quarters. Even though there's 5 numbers, it's 4 quarters. So, what percent of the data is less than 6? 50%. What percent of the data is less than 9? 75%. What percent of the data is greater than 2? 75. Very good. Do you guys have any questions on how this works?
Nah.
All right. Are you okay with the fact that this is 25% and it's only a difference of 1, and this is 25% and it's a difference of 2? You guys okay with that? Do you know why that is? Because it's in percentages. It's 25% of the data and 25% of the data. It's okay if they're spaced out differently. How do I show visually a 5-number summary? A box plot. You guys have probably called these box and whisker plots.
I've never seen this before.
You guys have seen these before.
No, I've never seen them.
Totally. All right, so this is the minimum. That's the minimum. The bottom part of the box is Q1. The middle of the box is the median. The upper part of the box is Q3. And the top of the whisker is the maximum. Can you visually see the IQR?
Yes.
The box itself is the IQR.
This hurts my eyes because I feel like something should be in the box. It should be in the box.
Nah. Now, I have bad news for you. Box plots come in all shapes and sizes. So here's another very normal looking box plot.
Okay, what?
There's another box plot. So, what's going on here? What is the star for? Very good. That star is an actual official outlier. It is an actual outlier. Guess what? It is also the minimum of this data set. It is a minimum, but it has been identified as an outlier. The top or the bottom part of the box right here, this is Q1. This line is the median. This upper part of the box is Q3. And since there's not an upper outlier, then the top of the whisker is the maximum.
Is it skewed?
It is skewed, very much so. It is skewed to the right, very good. Now, what about this bottom whisker? What does this number represent right here? What is that?
The last number before the outline.
You are so right. Very good. This is the lowest non-outlier value. That's the lowest non-outlier value. Here's the deal. It does not become a part of the 5-number summary. We would still just use the minimum, Q1, the median, Q3, and the maximum in our 5-number summary. But visually speaking, we do show it as the lowest non-outlier value. Make sense?
Yeah.
Any questions? All right, I have a question for you. What percent of the data is between the minimum and Q1?
25.
What percent of the data is here? What percent of the data is here? What percent is here? But guys, wait a second. This is way bigger than this. What happened? There's a whole lot of data stacked up here. There's a whole lot of data put together and compressed right here in this little section. This data is a little bit more spread out, but it's still 25% of the data. Does that make sense? Do you have any questions? Box plots. How do you make a box plot? Here it is. You're going to scale and label the horizontal axis, starting with the minimum number and going to the maximum number in even increments. So you make the scale first, then you start drawing the box. I know I didn't make a scale on my box, but that's fine. You'll see it later. All right, a box plot is made up of the numbers of the 5-number summary. A central box is drawn from the first quartile to the third quartile. Oh, wow, thanks. A line in the box marks the median. Lines called whiskers extend from the box out to the smallest and largest observations that are not outliers, and then outliers are marked with a special symbol or asterisk. That's it. Any questions? Don't worry, we're going to make several box plots on Monday, so it's going to be fine. But before we do that, we're going to talk about how to identify something as an outlier. So far, how have we said an outlier is identified?
A value that's deviates too far.
Yeah, it's just a value that is visually too far away from the data, right? It's like there's a big gap, and then you see this outlier sitting there, and you're like, oh, that's an outlier. So it is an unusually small or large value. So, okay, that's what we've been doing, but you guys are now older and wiser. You are older and wiser.
No, I'm not.
So, we are now going to identify outliers mathematically. We're going to use the 1.5 IQR rule. The 1.5 IQR rule. So, how does it work? First of all, find the IQR. How do you find the IQR? Q3 minus Q1. Perfect. Then, multiply 1.5 times the IQR. You're going to multiply 1.5 times the IQR. There is not a fancy name for that number. It is just the 1.5 IQR number. It's just that. I got nothing better than that. You can call it George if you want. I don't care. All right, so you're going to take Q1 and you're going to subtract the 1.5 IQR number. Anything lower is a true lower outlier. So you take Q1 and you subtract 1.5 times the IQR value. Anything lower than that, truly lower than that. So if it's equal, it's not an outlier. Anything truly lower than that is a true outlier. Any ideas how to identify an upper outlier? Good. Q3 plus 1.5 IQR. And anything higher is a true upper outlier. And that, my friends, is how you identify a true outlier mathematically speaking.